Before I continue in the solution to this problem, I want to shout out to this young man. His name is Somto. He's currently in chemical engineering from Futo, and he has been of great help in supplying me with questions and possible challenges that students would encounter in, engineering mathematics. So he's currently the academic coordinator of All Saints Chapel, which I passed through. So I want to really shout out to him and to every other person who has been supportive in helping out to set this tutorial up and in sharing the tutorials too. So well done, guys. I wish you all the best.
Hello guys, and welcome to the video you've been waiting for on Lagrange interpolation and numerical differentiation. So this is a 2-in-1 video. I'll try as much as possible to be quick, but if it is long, just know that it's because I'm trying to explain to a level that you can understand. Now we're going to be looking at the second part of the question that we solved just before this one. So if you want to find out the solution to this particular A part, you can check my playlist and you will discover how I used Newton interpolatory division. I gave a full detailed explanation of how to go about it so that you can approximate these values. Now, the second part of the question says, with this same table, evaluate dy dx when x is 0.26 using the 3-point Lagrange interpolation. So the big question is, how exactly or how on earth do we go about this process? So we're going to find out together. So solution. So my focus is on the second part. Now, before I dive into the solution, permit me to give you a background for the benefit of those of you who do not really understand Lagrange interpolation. Now, we can use Lagrange interpolation to interpolate for the values of this problem, just like we used Newton's interpolatory division. And if you understand Lagrange interpolation, if you use Lagrange interpolation and solve this problem for f of 0.05, f of 0.7, and f of 0.43, you're going to get just approximately the same answers that you got when you use Newton's interpolatory division method. So the Lagrange interpolation is another excellent and accurate way of interpolating values. Now, Lagrange interpolation does not just stop at interpolating values, it also helps us to carry out what we call numerical differentiation. So let me give you the background of the Lagrange polynomial. The Lagrange polynomial is called the n plus 1 point formula. So the Lagrange polynomial is called the n plus 1 point formula. So why it is called the n plus 1 point formula is because the polynomial of order n, of course Pn of x, is given to me as you can see summation k equal to 0. Then we are going to n, and we now have f of x k, and we now have l n comma k of x. So this is the Lagrange polynomial. So this is the formula that we call the n.1 point formula. So the formula will look intimidating at first, but let's assume, let me tell you why we call it the n plus 1 point formula. Let's assume you want to get a polynomial of order 3. Is that okay? You want to get a polynomial of order 3. That means or let me start with a polynomial of order 1. A polynomial of order 1 implies that n is equal to 1. Okay, so this is a straight line. Now this is how it's going to be. So p1 of x is going to be summation k equal to 0 to 1. Then you now have your f x k, and you now have your l, which is 1 constant, and you now have your k of x. So this x that you're seeing is the value that you want to evaluate, is the unknown. Okay, so let's expand this polynomial starting from k equal to 0 to k equal to 1. So when k is equal to 0, we have f, okay, x naught. You now have L10 of x, L10 of x, then plus, when k is 1, you will have f of x1, and you now have what? L11 of x. Okay, so this is what we call a polynomial of order 1, p1 of x, or a straight line. Now this is the equation of a straight line. Of course, you'll be very surprised to find out that there's another equation of the straight line apart from the y equal to mx plus c. So this Lagrange polynomial gives us another way of expressing the equation of straight line. This f of x naught and f of x1 are actually constants. In fact, they are ordinates corresponding to the points x naught and x1 where this line passes through. So the line passes through the points x naught, f of x naught, then x1, f of x1 in this case. So any line that passes through points x naught, f of x naught, x1, f of x1 is governed by this particular equation. Now, the most interesting part about this is what is the value of this guy and what is the value of this guy. Now, let me explain how you build the value of this guy. So p1 of x is the same thing as you having f of what? X naught, which is a constant. So L1 of x is a Lagrange polynomial. It's a Lagrange polynomial that you can form by subtracting your x, which is your unknown point, from every other point apart from this one, apart from a point with this index. So when I'm on x naught, I'm going to subtract x from every other point apart from x naught, which in this case is x1. Then I'm now going to replace this one in the denominator with x naught. Then I'll leave this one like that, x1. So this is how I've built this. Then let's repeat the process here so that you understand. So f of x1, okay, then you now have what? To form the L of x, you have to subtract x from every other point apart from x1. So every other point apart from x1, what exactly do I mean? Remember that this Lagrange polynomial of order 1 gives rise to two different parts. Okay, two different parts. So this Lagrange polynomial of order 1 is a polynomial that is actually built around 2 points. Okay, around 2 points. So that's why we call it the n plus 1 point formula. When n is actually 1, that means you're dealing with 2 points. When n is 2, you're dealing with 3 points, and so on and so forth. So when n is 4, you're dealing with 5 points. Is that okay? So if we are building this polynomial just like we did for this one, you're going to subtract x from all other points apart from this one in your first order system, and the only point apart from x1 is x naught. And you're now going to replace this one with x1 minus x naught. So if you expand this particular equation, you discover that you're going to get a straight line. So this is a straight line. So if they say find the equation of a line passing through 2 points, and they gave you the 2 points, you can actually use this particular build up to evaluate the equation of a line passing through 2 points. So let's build a two order system. Okay, let's build a two order system. So we're going to build n equal to 2. So for n equal to 2, my p2 of x is going to be we have summation k equal to 0. We now have 2. We now have f of x k, and we now have L 2 comma k of x. So this is how we're going to build it. So for p2 of x, we're going to have what? How many expansions? The number of expansions tells me the number of points we're dealing with in this case. So for the first order system, we had 2 expansions. 2 expansions corresponds to 2 different points. So let's see how many expansions that will result from expanding this particular build up that we have here. So this will give me f of x naught. Then we might have my L2 naught of x. Then plus when k is 1, f of x1, my L2 1 of x. And finally, when k is 2, you have f of x2. You now have your L2 2 of x. So if you follow the same pattern, p of x2, you can now agree with me that since there are 3 expansions, that means this p of x2, this polynomial in order 2, is built from 3 points. So that's why we call it the n plus 1 point formula. If the order is n, then the number of points is what? N plus 1, which is what? 3 points. Is that okay? That's why they call it the n plus 1 point formula. Now, let's try to find the polynomials for this Lagrange expression so far. So you have your f of x naught, which is the ordinate for the first point. F of x1 is the ordinate for the second point, and f of x2 is the ordinate for the third point. Now, if you expand this particular guy, what we are doing is we are subtracting x from every other point apart from x naught in the system. So we have 3 points: x naught, x1, and x2. Okay, so these are the 3 points we're interested in. So x will be subtracted from every other point apart from x naught, which is x minus x1, x minus x2. Then in the denominator, just replace this one with x naught. That's the point in question, x naught. Then this one stays as x1, and here is x naught minus x2. So this is how you've built this second order Lagrange polynomial for this first term. Then if you do the same thing in the second term, f of x1. Okay, so if you want to build the polynomial that is associated with L21, what you're doing is for this x, you're subtracting x from all points apart from x1 in your system. So you have 3 points, so you subtract it from x0 and you subtract it from x2. Okay, and you now what? Divide by, replace this one with x1 minus x0, replace this one with x1 minus x2. Then finally, for f of x2, who can tell me what it's going to give me? So it's going to give me, very good, you have x minus x0, x minus x1 divided by x2 minus x0 and x2 minus x1. So this is how to build your Lagrange polynomial. So this is how to build your n order Lagrange polynomial. So this is a second order Lagrange polynomial. Now this that you see here is another way for writing the equation of a second order or a second degree system, which is a parabola. So the normal equation of a parabola is ax squared plus bx plus c. Okay, that's the normal equation that we know. But this Lagrange polynomial expression here gives us the equation of a parabola passing through 3 points. Okay, so this is just about the Lagrange polynomial. Now, the Lagrange polynomial helps us to interpolate for values. If we know how to build the polynomial, we are very good to go. So, if you're given a particular question and you're asked to solve it using Lagrange interpolation, like let me go to this particular question, and they ask me to solve for all these values using Lagrange interpolation, and they ask me to use a 3 points Lagrange interpolation. 3 points. So if they say 3 points, I'll ask myself, for these 3 points, what will n be? n will be equal to what? Definitely n will be 3 minus 1 equal to 2, because the n gives me the order of the Lagrange polynomial that I will use to evaluate this 3-point question. Is that okay? Remember, we established the Lagrange formula as the n plus 1 point formula, whereby if you're given a particular order, let's say when the order is 2, you're going to have 3 points, or you're going to have 2 plus 1 point, which is 3 points, or you're going to have 3 expanded terms, and the 3 expanded terms will contain the ordinates of the 3 points that you're actually dealing with. Is that okay? Now we are going to for the purpose of this video, restrict our study to the 3-point Lagrange formula. Okay, the 3-point Lagrange formula and the 3-point method of evaluating derivatives. So I'm going to write it again so that you understand how to derive it, even though you're in an exam situation. So how do we obtain f of x? Okay, how do we obtain f prime of x? That's the derivative f prime of x using Lagrange polynomial. So how do you obtain f prime of x using Lagrange polynomial? If you want to obtain f prime of x using Lagrange polynomial, so we're using Lagrange polynomial, that's the 3 points. So first of all, you need to be able to know what brings about 3 points. What brings about 3 points is when the order of our system is 2. So that means we are dealing with a polynomial of second order. Now, let me just call it, we can use p, we can use f. So we can call it f2 of x is equal to this polynomial that we saw here. That's the summation k equal to 0 down to 2, and you now have your f of xk, and you now have your L2, which is the order, then you now have k of x. All right, so follow me gradually. Remember that when we built this polynomial, our f2 of x became what? You had f of x naught. We now have our L2 naught of x. Then we now have plus f of x1, our L2 1 of x, and plus f of x2, which is our L2 2 of x. So when we actually built these guys, we have our f2 of x, second order polynomial, is going to be f of x naught. Then we're now going to find this one by subtracting all points apart from x naught in the system. Remember, you have 3 points: x naught, x1, x2, x naught, x1, x2, which we are going to definitely know from the tables given to us. So subtract x from all points apart from x naught, giving you x minus x1, x minus x2. Then the denominator, just replace x with what? X naught. That's this one, minus x1, and x naught minus x2, and you now have plus your f of what? X naught, right? And you now have f of x1 in this case. Then you now have x minus x naught, x minus x2, all over x1 minus x naught, x1 minus x2. Then finally plus f of what? X2. And you now have your x minus x1 and x minus x naught first, then x minus x1, all over x2 minus x naught, x2 minus x1. I hope that's what I did up there. Okay, very good. So this is how to build your polynomial. You understand that for x2, there is no term x2 here in the numerator position, because you're subtracting x from every other point apart from x2. In the denominator, it will just take exactly the same form, only that you replace this x with x2, which is the point in question for this particular term. Now you've been able to build this polynomial. Now this is what we call the 3-point Lagrange interpolation polynomial. So this is your 3-point Lagrange interpolation polynomial. 3 points Lagrange. So after you've done it like this, now if you've gotten your 3 points, how do you actually get the derivative? So f prime of what? X2. Okay, in other words, or f prime of x. How do you differentiate this? So what is it going to be? Now, before we actually go on with the differentiation of this one, I want you to know that this is actually the same thing. This your f2 of x is going to be the same thing as your f of x naught. If I expand this guy, what I'm going to get is I'm going to get x squared minus x1 plus x2, okay, x then plus x1 x2, like this. So I'm using the rule that x minus a, x minus b is equivalent to x squared minus a plus b x then plus ab. So that's what I'm using for this particular scenario. So let me make it much more smaller. All right. So we'll have x squared, all right, then minus x1 plus x2 x, then you now have plus x1 x2, then all over the same denominator you have x naught minus x1 and x naught minus x2. Is that okay? That's for this term. Then for the next term, you will have f of x1 into this. When you expand it, you get another x squared minus, so the two terms in the bracket is x naught plus x2 x, and you now have plus x naught x2 all over x1 minus x naught x1 minus x2. Then finally, we'll now have plus f of x2. I can form it with my mind, so it will be x squared minus all the sum of all points apart from x2, which is x0 plus x1, and the product of all points apart from x2 is x0 times x1. All over we have x2 minus x0 x2 minus x1. Okay, so this is your 3-point Lagrange polynomial, another form of expressing it, and you can see that it confirmed what we said earlier, that the 3-point Lagrange polynomial or a second order Lagrange polynomial gives us a parabola. Now, what are the constants in this equation? The constants are f of x0, f of x1, f of x2, then x1 x2 is a constant. The whole denominator is a constant because x1 x0, x1, x2, all of them are known. So you know x1, x2, and x0. You know the f of x0, you know the f of x1, and you know the what? F of x2. You know all these points because you'll be given a table, okay, containing all of them. So the only thing that is a variable here is x. Anywhere you see x, that's the only variable. Apart from that, every other thing is constant. So this now leads us to be able to find the first derivative of this particular term. So my f1, okay, f prime of x2, okay, in other words, dy dx is going to be, so if we differentiate, all constants will remain as they are. So f of x naught is a constant, and the denominator will remain as it is, x naught minus x1 x naught minus x2. So what happens to the numerator? Differentiating x squared, you get 2x. Then differentiating this term, this is a constant, so it will cancel out. So when you differentiate any term in x, only the coefficients will come out. So 2x minus x1 plus x2. Okay, so 2x minus x1 plus x2 still evaluates to 2x minus x1 minus x2. Is that okay? Then you now have, if you repeat this step in the other terms, you have plus f of x1 is a constant, then the denominator remains as it is. They are also constants. Then you now have x1 minus x2. So if you differentiate the numerator, you're going to have what? You're going to have 2x minus. So if you repeat the same thing, differentiate this one, you just get these brackets, okay, only these brackets, and this term will cancel out. So when you open this bracket with a negative sign, you get x naught minus x2. Is that okay? And finally, plus f of x2. When we repeat the same pattern, we are just subtracting from 2x all terms apart from x2, which is x0 and x1, and we are dividing by the difference between x2 minus x0 and x2 minus x1. Is that okay? So this is how to build a 3-point Lagrange what? Polynomial for f prime of x. So what have we achieved in this video? In this video, we've achieved two things. The first thing we've achieved is we've learned the form of the 3-point polynomial for approximating the value of f of x. So to approximate the value of f of x, all you just need to know is this polynomial. So any x they give you, just plug in the value of x here. Okay, then every other thing will be given from the table that you're using. You could just quickly extract those values from the table and plug it in and resolve. Is that okay? So we have also secondly found the derivative for 3-point formula. So for 3-point formula, this is the derivative. Now I'm not expecting you to derive this in the exam hall. If you can derive it, good and fine, but it's good you know how to derive it so that if you forget, you can easily come up with the formula. So the reason why I taught you up to this extent is so that you can know that this is the formula that we are going to use to solve this question. So had it been you knew this formula of heart, you could just easily have used it, okay, to approximate the value of this particular problem. But for the sake of those who have not learned anything about Lagrange, this is the formula for f prime. This one is the formula for f prime, that's interpolating for f prime, and this one is interpolating for f of x. Okay, so Lagrange can be used for interpolating both the point and the derivative of a function at a point. So that's why it's a widely used formula. So this is the 3-point Lagrange formula, okay, for f prime of x. So that's what we are going to use to solve this problem. Now let's dive into the solution of that problem. So let me just copy it out. So this is the formula that we got previously. So how do we use it to solve that problem? They want us to solve for dy dx at 0.26. This is still corresponding to f prime of 0.26. Is that okay? So all we just need to do is to what? Find 3 points in the neighborhood of 0.26. So find 3 points in the neighborhood of 0.26 and use those 3 points to approximate the first derivative of this function at what? 0.26. So what I'm going to need again is I'm going to need the table. I'm just going to copy the table out here. So this is the table we're given. I've copied it out, and let's get back to where we were. I'm going to paste the table here. All right, so let's select 3 points in the neighborhood of 0.26. So in the neighborhood of 0.26, I can see that I have the liberty of choosing for 3 points. I can choose this one as my x0, I can choose this one as my x1, I can choose this one as my x2, because these 3 points are in the neighborhood of 0.26. So the point that is closest to 0.26 is 0.2. It's closest from the left. Is that okay? So 0.2, then you can use 0.2, and 0.4. So someone else can decide to, for this particular point, for this particular arrangement, he could decide to choose his 3 points as 0.2, then 0.4, and 0.6. Okay, so your x0, x1, x2 is 0.2, 0.4, 0.6. So these are the 3 points that you'll be working with. Okay, so by 3 points I mean the value of x and the corresponding value of y. So that's what we call the 3-point Lagrange formula. So which one are we going to use? So I'm going to give you an assignment. So in this video I'm going to use this as my 3 points, 0.2, 0.4, 0.6 as my 3 points. Then in your own practice time, you're going to use 0, then 0.2 and 0.4. Okay, so this is for your assignment. So you compare whatever answer I get with the one that you get, and we are going to see how well it works. Is that okay? So let's dive into the solution. So we know that our f prime of x, the polynomial, is given to us as f of x naught. You can build the polynomial by yourself. Then you now have 2x, so minus subtracting every point apart from x naught, which is x1 and x2, then all over x naught minus x1, x naught minus x2, then plus f of x1. Then I'll have 2x, subtract every point apart from x1, which is what? X naught and x2. Then you have x1 minus x naught, x1 minus x2, then plus f of x2, and you now have 2x, subtract every point apart from x2, which is x naught and x1, and you now have your x1 minus x2 minus x naught and x2 minus what? X1. Are we together? So this is for the derivative. Remember, the f for the derivative is different for the f for normal interpolation. So this is the f for normal interpolation, just like we established here, the one that you use for normal interpolation when you're giving, let's say you want to use 3 points Lagrange formula to interpolate for a particular value. So you use this one for normal interpolation. Is that okay? So this is for normal interpolation. So in order to get the one for derivative, we differentiated this guy and we got this pattern over here. So that is what we now want to use to solve this question. So if you're ready with me, we can jump into the solution. My f prime of 0.26, that's the derivative at 0.26, is now going to be, you have, for this one you use f of x naught. Remember, I'm going to take this section of the table. I'm taking this section of the table, I'm using it as my 3 points. But for your assignment, your 3 points is from here to here. Is that okay? But my 3 points is this, this, and this. So I label this as x naught, label this at x1, and label this at x2. So I have f of x naught. So my f of x naught in this case, right? Since I'm taking this as x naught, my f of x naught is 1.22140, then multiplied by 2 into 0.26 minus. So you could just easily use your calculator to set this up. I'm just going to write it so that you understand what is happening. So my x1 is 0.4 minus my x2 is 0.6, and divided by x naught is 0.2 minus 0.4. You now have 0.2 minus 0.6. So this is for this term. Okay, then plus my f of x1. My f of x1 is, since this is my x1, this is my f of x1, which is 1.49182, then multiplied by 2 into x. 2x is 0. What? 26. That's the derivative we want to evaluate. And you now have minus x naught, which is 0.2, minus x2, which is 0.6, and all over x1 minus x naught, which is 0.4 minus 0.2, and x1 minus x2, which is 0.4 minus 0.6. Is that okay? Then finally, plus your x2 or your f of x2. F of x2 is going to be this guy over here, which is 1.82212. You have 1.82212, and you now have 2 into 0.26. Okay, you're going to subtract. For your x2 is what? 0.6. So subtract other points apart from 0.6, which is 0.2 and 0.4, since you chose those three. And you now have 0.6 minus 0.2 and 0.6 minus 0.4. Is that okay? So let's set up our calculator and evaluate this. So setting up our calculator, we are going to have 1.2140 times, open a bracket, and in the bracket you put 2 into 0.26, and you have minus 0.4 minus 0.6 divided by what? The first bracket is 0.2 minus 0.4, and second bracket is 0.2 minus 0.6, like this. Is that okay? So you're satisfied for this first term over here. So you go to the next one, and I have plus. We have 1.49182 times, open the bracket, and repeat the same thing. We'll have 2 into 0.26, and you now have minus. We have 0.2 minus 0.6, and the base we have 0.4 minus 0.4 minus 0.2 times 0.4 minus 0.6, and we now have plus. Okay, then finally 1.82212 times, open brackets, you put the fraction, and you have 2 times 0.26, okay, minus 0. Definitely to be 0.2 minus 0.4, and 0.2 minus 0.4, and we now have 0.6 minus 0.2 times 0.6 minus 0.4. So let me just make some corrections before I actually solve. I didn't put a times here, so it will give me an error. The same thing, supposed to be a times here. So we've set it up, and we are ready to press evaluate. So can you see? So we have 1.29222. So f prime of 0.26 is approximately 1.29222. So that's the value that you will get. So remember, for your assignments, you're going to use, instead of this as your x naught, instead of this section as your 3.123, you're going to use this other section as your 3 points. Okay, since these 3 points are around 0.26. So any question they give you and they ask you to find f of something, you're going to actually focus with Lagrange 3 points formula, focus on those data in the table that are around the neighborhood of that point. Is that okay? So that's how we are going to be able to resolve this problem. So try to solve with these 3 points and compare the answer that you get to the one I get, and see if it's approximate. So I believe if you do everything correctly, you should get an approximate value of what I have here, at least to two or to one decimal place. It should be approximate. So this is about Lagrange interpolation, the numerical differentiation using Lagrange interpolation, numerical differentiation using Lagrange interpolation. The Lagrange plus 1 point formula have been extended to include some other numerical differentiation formulas that we will actually find useful. So there are other numerical differentiation formulas which I believe you must have seen before. There's one called the 3 points, the 3 points midpoint formula. Okay, so the 3 point midpoint formula is given to us as f prime of x is equal to 1 over 2h into f of x naught plus h and minus f of x naught minus h. Is that okay? Then you now have plus an error term. So approximately we can just leave it as 1 over 2h into f of x naught plus h minus f of x naught minus h. Is that okay? So I'll explain when you're to use this formula instead of the Lagrange 3 point interpolation formula that we just used above. So this is a 3 point midpoint formula. Then there is also the 5 point midpoint formula. The 5 point midpoint formula. So if you want to solve for the 5 point midpoint formula, you're going to have that your f prime of x is going to be approximately, let me remove the error term, 1 all over 12h, and you now have f of x naught minus 2h, then minus 8 f of x naught minus h plus 8 f of x naught plus h, then minus f of x naught plus 2h. Okay, so this is the 5 point midpoint formula. So what do you have in common between the 3 point and the 5 point midpoint formulas? For the 3 point formula, you just have two terms in the brackets. So they're just trying to tell us that if they give me 3 points, okay, an x naught minus h, then an x naught plus h, okay, then I can just focus on using the f of this x naught minus h and the f of x naught plus h around the vicinity of this particular point f of x. Now the only time that you use this 3 point midpoint formula is if they ask you to evaluate the integral, the numerical differential of a particular table of data, given that the points are evenly spaced with some particular interval h. So they will specify the value of h that you should use. Okay, when they specify the value of h that you should use, you can now plug it into this formula, okay, around the vicinity of the points that you're interested in. When you plug it in this formula, you're going to get some things, and eventually you use it to evaluate for the first derivative of the function at that unknown point. So I'm just introducing these formulas here, but I hope to solve an example in another video. So there is also second derivative, okay, the second derivative or higher derivatives. So for higher derivatives, what you should be focused on for higher derivatives is just the second derivative, so f prime prime of x. So we combined the Lagrange polynomial and the our Taylor series, and we got that our f prime prime of x can be written as 1 over h squared into, I have my f of x naught minus h, then you now have minus 2 f of x naught, you now have plus f of x naught plus h. Okay, so this is for second derivative. So these are the three formulas that you should pay attention to when you're giving numerical differentiation, in addition to the one that I have already showed you here from the past question. So in another video, I'll try to solve one or two examples with the 3-point midpoint formula, the 5-point midpoint formula, and the one for higher derivatives. I'll try to solve and show you how to use them. Now, some of you might be asking, why didn't I use this particular one to solve this particular problem? Well, I couldn't use it to solve this problem because the condition for using this 3-point midpoint formula is that if they ask me to find derivative of a function at a particular point, they must in the question specify the value of h. What is h? Is h 0.2, or is h 0.01, or is h 0.1? Okay, now in the question that we were given, if you look at the question very carefully, they never specified the value of h. They just said find the derivative, that's the f prime of x, at this particular point using 3-point Lagrange. Now they didn't specify the value of h. Okay, so h was not specified. So had it been specified the value of h, then I would know that I can easily use the 3 points instead of the Lagrange interpolation. I'll use 3-point midpoint formula to solve it, which will be relatively faster than the Lagrange approach. But anytime they never specify the value of h, they didn't specify it, they just said using the 3-point Lagrange interpolation, what you're going to do is to try to derive this polynomial, or try to memorize this polynomial that I gave you here. Okay, try to memorize it or understand the pattern. So this one does not require h, whether h or no h, it doesn't really depend on it. You can use it whether the points you're giving are spaced evenly or not. So one of the benefits of using Lagrange interpolation is that there are sometimes they'll give you some data sets, you see these values are evenly spaced, is that okay, with 0.2. So there are some data sets that will not be evenly spaced, and you can still use Lagrange interpolation to approximate the value perfectly, okay, to a perfect approximate value. So that's the benefit of Lagrange interpolation. Now, another reason why I cannot use the 3-point midpoint formula here is, even though in this particular question h is 0.2, that's the interval between these points are 0.2, but look at what they want me to find, 0.26. I can't, no matter how I add 0.2 to this point, there is no way I can get 0.26. So it's not possible. If you want to solve, let's say your x naught is 0.26. Is that okay? This is your x naught. And let's say your h is 0.2. If you want to use the 3-point midpoint formula, you need to solve for f of x naught plus h and f of x naught minus h. Okay, so minus this plus this. So you need to actually solve it, and if we want to solve it, we'll now have to find f of 0.26 plus 0.2 and f of 0.26 minus 0.2. 0.26 plus 0.2 is f of 0.46, and 0.26 minus 0.2 will be a 0.06. Now, the essence of using this 3-point midpoint formula, okay, that I showed you in the other screen, was for you, after performing this x naught plus h, the value that you get must be present in the table. It must be present in the table so that you can read it off. Now, this value that I get from 0.26 plus 0.2, you can see 0.46, and it does not exist in this table. Neither does 0.06 exist in this table. So there's no way I can use the the Lagrange 3-point midpoint formula. There's no way I can use it. Okay, that's the midpoint formula, but you can just use the 3-point Lagrange interpolation. That's the general expression. Okay, that's this one over here. Now I want you to know that that 3-point midpoint formula, that one that you saw, was actually derived from this one. So it was derived when you have evenly spaced intervals. All the intervals are separated from themselves by a distance of h. So they used this formula to derive this 3-point midpoint formula. The calculation is kind of like out of the scope of the video for this point, so I might not be able to do that now, but you just know that this formula that I showed you on green ink was what was used to derive this particular formula that you're seeing over here. So if you use a 5-point Lagrange pattern, you will be able to derive this other formula that is actually given here. Is that okay? So hopefully, if you have lecture notes that explain more on the use of the 3-point midpoint formula and the 5-point midpoint formula, follow them so that you can understand how they were solved. But this particular one, I solved it based on the exam scenario and the demand for your examination solution. And this one is purely dependent on the use of this general form, which you must know how to either memorize or know how to reproduce, so that you can be able to substitute the value that you're looking for and evaluate the solution thereabout. So we've come to the end of this lengthy video. The most important thing apart from the length is I hope you understood. So just remember how to obtain this or memorize it, and you'll be all right. So thank you very much for watching. Subscribe to my channel, hit the notification bell to stay updated, and share to your friends. So good luck, stay blessed.